It is an honor to give the first talk on intuitionistic logic at this conference. It is an enormous honor, but it is also a massive challenge. This means that people expect me to introduce intuitionistic logic. And of course, a lot of you are experts in intuitionistic logic, and maybe have read the paper this is about, and they're eager to hear the technical details. And some others might not know about intuitionistic logic at all, and therefore want some kind of context and explanation of what the heck is going to happen. So I have to get everybody on the same page, and then I have to present cutting-edge research, and all in 25 minutes, which is quite challenging. So I opted for a compromise solution. Half of my talk is going to be too fast, and half of my talk is going to be too slow. And I run out of time and fail to present the last 5 slides. And if this actually happens, don't say that this was a bad talk, right? That was the plan. Okay, so let's meet in the middle. We all know classical logic at this conference. And we know that classical logic allows us to prove the law of excluded middle for all propositions P. That's the law of excluded middle, P or not P, there in the middle, just in case there's any ambiguity with that, hopefully not. And we have intuitionistic logic, which allows us to prove the law of excluded middle for some propositions P only. Which ones? Well, if you don't know, this is not the right time to learn that. It's outside the scope of these 25 minutes. Instead, I want to talk about something quantitative. How many propositions satisfy P or not P in intuitionistic logic? And my goal is to obtain a surprising sort of dichotomy result between classical logic and intuitionistic logic. Where in the classical case, of course, every proposition satisfies P or not P. And I want to show in various ways that in some sense, very few satisfy P or not P in intuitionistic logic. So philosophically, this is that the classical world looks very, very different from the intuitionistic world. They're easy to tell apart. There is no world which looks mostly classical, except that excluded middle fails for one proposition in 10 billion or something like that. If the law of excluded middle fails, it fails big. And these results that I present are fairly stable in that, well, there's that weasel word, very few there. But these sorts of results, as you'll see, seem to hold no matter how you formalize most propositions or many propositions or very few propositions. No matter how you do that, it's always true that in this sense, very few will satisfy P or not P. So credit where credit's due. Most of today's talk is based on an article which appeared in JSL this year, and it is joint work with Ben Wampus, who's in Sao Paulo now, I think. And I'll also be announcing some results I obtained since then. Those are me, and if they're wrong, since I haven't written them up yet, then it's all on me, right? And some others have picked up this sort of thing. Matt Evans, who's in Pennsylvania, Washington, Jefferson College, I think, has an article about the same sort of phenomenon in BCK algebras. And I don't want to talk about BCK algebras today, so that's all I'm going to say. But he has a great talk on YouTube, which you can watch if you want more of this material. Okay, so how are we going to talk about the very few propositions? Well, in the article, we proposed an algebraic approach. We're going to say, well, let's take intuitionistic logic. Let's take an algebraic semantics for intuitionistic logic, which most of you will know how that goes. That's hating algebras. That's the standard semantics for indigenistic logic in an algebraic setting. And once we obtain that, we're just going to count the number of solutions to the equation x or not x equals top. And we'll think about these points we solve this equation as sort of propositions. Before I do that, I'm going to explain how this is done in other fields of math, in algebra. How do people like to study the sizes of solution sets of equations? So if you've taken any group theory, some of you haven't, it's all right. You can tune out for a bit or not. I suggest not. You know that if in a group x squared equals the identity for all x, then that group G is in fact an abelian, meaning that xy also equals yx for all elements. So if every element solves that equation over there, then every element solves that equation over there. But a lot fewer people know that there's an approximate version of this result as well. We start with a finite group G, and you notice that more than 3/4 of the group solve this equation. Then in fact, all elements of the group solve that equation. So there's a sort of weird gap there. Cannot be that 99% of group elements solve this equation, but some don't. If more than 75% solve the equation, then all elements solve the equation. And this is what this theorem states. You can also think of this probabilistically. You can say, well, if I have this group and I pick a random x and evaluate x squared, then I won't get 1 with high probability, right? With probability greater than or equal to 1/4. And here's a more well-known result of the same type, which is due to Gustafsson from 1973. You take this equation, xy equals yx, and you count the number of pairs xy which satisfy this equation, then either less than 5/8 of those pairs, of all possible pairs, will solve the equation, or else all pairs solve this equation. Again, we have this sort of gap. There is no group in which is deceptively abelian in some sense, where most elements solve this equation, but not all of them do. And if you think back to what I said a few slides earlier, this is exactly the sort of dichotomy result we're looking for, where something either happens always, such as x or not x always folds in classical logic, or it happens very few times, right? With low probability. And you can phrase this problem generally. You can say, well, groups are a very specific structure that mathematicians are interested in. Maybe you're only interested in logical structures. Doesn't matter. Any kind of algebraic structure you can play this game in. In fact, any kind of first order structure you can play this game in. You fix a language, you fix an L structure, a finite L structure, of course, and you fix some property, and you count how many n tuples satisfy that property, and you call that the degree of satisfiability of that property. All right, and it's going to be a number between 0 and 1. It's essentially the probability that if you pick random elements from your structure, you get something which satisfies that property. And if you generalize this, you see that this phenomenon which happened with these group equations actually is quite rare. So you give it a specific name. If you can find some constant epsilon such that in every finite model, everything satisfies phi, or else only few elements, less than 1 minus epsilon, times the size of the structure satisfy phi, then you say that the formula has a finite satisfiability gap. The gap itself is epsilon, right? Like it can't be epsilon close to satisfying this property. And so for x squared equals 1. Epsilon is 1/4. That's easy. And in group theory, you can test other equations and you get other results and you get unknown results, right? Like nobody knows what happens with x to the 5 equals 1. If you look at those numbers that come earlier, you might have a guess of what should happen. And we know that doesn't happen, right? We know something else happens, but that's all we know. And the reason I knew about this is that I proved some such results during my PhD. That was a long time ago for various equations. And this is not a toy property, by the way. Algebraists take this seriously. And if you know group theory, you can see what kind of structural information you can deduce from this. I won't talk about that for now. Instead, I will talk about degree of satisfiability in Hating algebras. Now, Hating algebra is a bounded lattice with an additional operation arrow, which models intuitionistic implication, and it's defined by this like sort of a joint condition. But it also has a simple algebraic presentation, and you can see that it's quite sensible. Like this just says if x holds and x implies y, then x and y hold. And you can read the rest similarly, okay? And the reason these are important is that these are the standard algebraic semantics for intuitionistic propositional logic. Formula phi is a tautology of intuitionistic propositional logic, precisely the corresponding equation in every Hating algebra constitutes an identity. So the corresponding equation is satisfied by all elements in every Hating algebra. And a classical principle is an equation which is satisfied precisely in those Hating algebras which are Boolean algebras. You all know Boolean algebras. They're the algebraic semantics of classical logic. If any one of these holds in a Hating algebra, then that Hating algebra is in fact a Boolean algebra. And then the main question is, well, how well can these classical principles hold in non-Boolean Hating algebras? So we refined our question to which equations have finite satisfiability gap in such algebras. Unfortunately, there's no time to present proofs. Okay. If you want to know how they are proved, talk to me. They have 3 different proofs and they generalize in 3 different ways. But our big result is that x or not x has a finite satisfiability gap, and it is 1/3. What does this mean? It means that if you choose a random element of the Hating algebra, it either always satisfies the excluded middle, in which case your Hating algebra is a Boolean algebra. You're back at classical logic. Or else very few of them do. Less than or equal to 2/3 of the random elements. And in fact, this is essentially the only equation in the language of Hating algebras which has this property. In group theory, we don't know which equations have this property. Here, in Hating algebras, we classified all of them, and we know which ones do have this property and which ones don't, and this is essentially the only equation. So there is a Hating algebra, for example, where not x or not x equals the top element very, very frequently. Like, say, for all but 0.001% of all propositions, but not always. However, there's no Hating algebra where the law of excluded middle holds for more than 66% of propositions, but not always. If it holds for a lot of propositions, it just holds always. So this not x or not x, this is actually equivalent to De Morgan's laws. So this basically says that, well, De Morgan's laws can be deceptively true. It might be true that if you look at random instances of De Morgan's law, they're almost always true. But there are some very weird, very rare counterexamples. But logic cannot be deceptively non-classical. If the logic you're investigating is intuitionistic but not classical, then there will be plenty of examples where you can see this. there will be plenty of examples. X or not X equals 1 will fail at. Okay? That's a mouthful. Like I'm feeling tired, and I just said it. So we can do a whole lot for multivariable equations as well. If you remember, if we go back to that slide with all the classical principles, like, you know, Peirce's law has two variables and so on. And turns out we can say quite a lot about the two variable case as well. Read the paper if you're interested in that. It's very, 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 very difficult, because we're using some properties of the free Heyting algebra on one generator to classify the one variable case. And the free Heyting algebra on two generators is extremely complicated. It's one of the most complicated common structures in mathematics, if I may say so. Every order theoretic phenomenon you can think of happens somewhere in the free Heyting algebra on two generators, right? Like that should give some context. And okay, so that's difficult. That's only like half done. We've proved some results, but we don't have a full classification. Chances are we never will. And by we, it's just not me and my co-author. I don't think anybody ever will have that. It's just too complicated. But okay, but you're probably not satisfied upon hearing this, because this is all very finite, right? Finite this, finite that, finite probabilities, but logic is not finite. Most Heyting algebras of interest are infinite. Intuitionistic logic is the algebraic theory of the free Heyting algebra on countably many generators. Even the generating set is not infinite, and the structure itself is not finite. Correction. Even the generating set is not finite, and the generated structure is very much non-finite, and it's very, very subtle, and it's very, very complicated. And that's what logic actually is. Like, you know, like these finite models are sort of toy models of this phenomenon. So what happens in the infinite case? Well, we have a big problem. We use the finiteness of these algebras to say, oh, you can pick a random element, just uniformly, just pick one of the finite many elements. And you can't do that in an infinite algebra. No natural notion of random element, and unlike in group theory, there's no natural notion of density either. So you don't have a good measure of how big a subset of a Heyting algebra is, unless the Heyting algebra is finite. So we had a crude idea while working on the finite case. Well, what if you just use cardinality? Almost whimsical. Surely that's not. Well, we said, yeah, let's say like, solution set to an equation is going to be large if it has larger cardinality than its complement. All right? Deceptively simple, and yeah, you'd think this would never work. And you can formalize this what I just said, larger cardinality than its complement, and it looks like this. You have an equation phi. Either the complement is empty, in which case your equation holds for all variables, for all values of variables, for all inputs. Or else there's an injective map from the solution set of the equation to its complement, right? In case one, it's big. In case two, it's small. And if this phenomenon happens, we say that there's an infinite satisfiability gap. Almost too naive, but it works. You get the exact same classification as in the finite case. The proofs are very different, right? You can no longer use anything that you used in the finite case. But the classification does work. And so you get that these equations have infinite satisfiability gap. You also get something very, very strong if law of excludability has finitely many non-solutions, so very few non-solutions, then your algebra itself is finite, right? And you get a nice corollary about topological spaces. If you're only interested in mathematics and you don't care about the rest, this is actually hard to prove without these results. So that's very nice. And yeah, the dual result holds as well. Like for all equations that are not those three above, we can find an infinite Heyting algebra where those equations only have finitely many non-solutions. So in the article, we construct these heading algebras with non-solutions using standard model theoretic techniques. We know how to construct finite examples, and we just use an ultra product to tie them together into infinite examples. Very simple, not very constructive.
Time. Oh, minimal case.
So most infinite heading algebras are wildly infinite. Thank you for John David Hankins for drawing this. This is the power set lattice of the naturals representation. It's not the whole thing, right? But you can see that this is quite a wild structure. And you know it's quite a wild structure. It is also a Heyting algebra. It is in fact a Boolean algebra, right? Okay, so most heading algebras are like this. They're super bad. They're very infinite and wildly infinite. And this includes the free and the finitely generated heading algebras that we actually want to study. And those present hard problems. So let's do something simple. Let's say something about tame infinite heading algebras. Infinite heading algebras that are so nice you can actually draw them on paper, like, you know, just by hand, and not have to think too badly about what goes where. So such tame heading algebras might have a less crude measure of size than just mere cardinality. And the early example of this phenomenon is, well, you look at the plane and you think about the solutions to the equation x squared plus y squared equals 1. This is the unit circle. If you know set theory, you know it has the same cardinality as the plane. But you also know that this is very small. It's very small. It's a one-dimensional set in the two-dimensional plane, right? So in like algebraic geometry and stuff like that, these dimension notions allow you to put aside on certain solution sets. So we consider heading algebras definable in an O-minimal structure. If you don't know what these are, again, this is not the time to learn them. Thursday is the time to learn them. Professor Conversano is giving a talk about them. It's going to be great. Be there. So these are the heading algebras we can draw, and definable subsets have a notion of dimension. And this is the usual notion of dimension that you think about. Right? This is a definable heading algebra. It's the product of the two-element Boolean algebra with the unit interval. Looks like this. You can actually draw it. This is if you think that these are related like vertically as well. This is essentially whatever it's called. You know, those diagrams for posets. I'm blanking on the term. Posset. Yeah, there you go. Essentially. And I highlighted the solutions to x or not x equals top with blue. There's just only 4 of them, these 4 points. So you get a very similar classification again. In an O-minimal structure, subsets defined by these equations have dimensions here. They're always just points. And for any other equation, we can find I'm missing a unequality sign here. That's unfortunate. I'll correct that in the final slides. We can find heading algebras where their non-solutions have maximum dimension. So in a two-dimensional algebra, the non-solutions have 2 dimensions, and in a 6-dimensional algebra, the non-solutions have 6 dimensions. But the whole algebra doesn't satisfy these things. So this is again a similar result, right? Like for excluded middle, there's only very few solutions, or else everything is a solution. And part 1 here is actually really simple. It's a Vapnik-Chervonenkis argument, which shows that you cannot define any infinite Boolean algebra in these structures. And of course, the elements which satisfy this would be an infinite Boolean algebra, so you can't have that. But part 2 is a nice construction. It upgrades our nasty model theoretic construction into a nice construction where you can actually draw these algebras. And when I say you can draw them, you can literally draw them. They on paper. I didn't do it here because I didn't have time. But trust me, you can do it. So that's 3 cases. That's 3 cases where these results hold. We don't know the most important case. right? The free Heyting algebra and countable many generators. We don't even know how to state that because that's a nasty structure. That's a very nasty structure. It's not definable in any omitable structure. The cardinality arguments are not really applicable. Well, they do yield something, but it's not really what we want. We want a somewhat technical generalization of the degree of satisfiability. I think I do have that, but I only have partial proofs. Everything gets very, very difficult. If you're up for a challenge, you know, talk to me. Yeah, there's philosophical motivations, logical anti-exceptionalism, that sort of stuff. I learned the hard way not to discuss this in front of a mathematical audience. So talk to me in the break if you're into that sort of stuff. Okay. Thank you so much.